we can use the molar mass of a compound to count the number of particles in a sample if we know its mass, or if we know how many particles we need, we can find out how much we need to weigh out. The molar mass of a compound is the mass of one mole of particles of that compound. And we usually write it down in grams. So for example, we could say that the molar mass of water is 18.0 grams or 18.0 grams per mole. If we need to, we can find out the molar mass of a compound using the chemical formula of the compound, and we need a periodic table. Here's an example of how we did this. There's a separate video in Mr. Field's Chem channel on YouTube about how to find the molar mass of a compound. So the molar mass of a compound, if we know the mass of a sample, we can figure out how many particles are in that, the number of moles of particles. If we want a certain number of particles, we can figure out how much mass we need to weigh out to get that number of particles. Let's do some examples. How many moles of water molecules are in 90 grams of water? The formula for water is H2O. There's the molar mass of water, 18.0 grams. So we can make a factor from the molar mass. We can put the number of grams on top and 1 mole on the bottom. We can equally validly make a factor with the 1 mole of H2O on the top and the 18.0 grams on the bottom. Those two measurements are related to each other. We can write the factor either way. So which factor are we going to use? Well, we need to look in our problem and see what our starting measurement is. In this case, it's 90 grams of water, and we want to figure out how many moles that is. So we're going to choose the factor that has the grams of H2O in the denominator. So we can do the arithmetic, 90 times 1 divided by 18, and that gives us 5, which is the number of moles of water in 90 grams. Does that make any sense? Well, for one thing, the units cancel out. The grams of H2O cancel out if we put grams in the denominator of our factor, and we have grams in our starting measurement. And it leaves us with moles of water, which is what we wanted to find out in this question. It also makes sense because the number of moles is much smaller than the number of grams. So 1 mole is smaller than the number of grams in a mole. So the number of moles in 90 grams ought to be much smaller than 90. Here's another example. How many moles of carbon dioxide molecules are in 176 grams of carbon dioxide? This time we don't know the molar mass, so we have to figure it out. So the molar mass of carbon dioxide is 44.0 grams per mole. We can make a factor out of that information. We can put the 1 mole on the bottom or the 1 mole on the top. Which factor are we going to use? Well, we go to our problem, our question. What is our starting measurement? 176 grams of CO2. So we want the factor with grams in the denominator. Our arithmetic is to multiply 176 times 1 and divide by 44. That gives us the number of moles of carbon dioxide in 176 grams. Does that make sense? Yes, our units cancel out correctly. And also yes, because the number of moles is much smaller than the number of grams. 1 mole is much smaller than the number of grams in 1 mole. So 4 moles ought to be much smaller than the number of grams in 4 moles. Here's another example. This time the question is different. This time we're finding out how many grams of methane, CH4, we have, and we're told how many moles we had. So if we wanted 9 moles of CH4, how many grams would we have to weigh out? We're given the molar mass of methane. We can write it with grams on top and 1 mole on the bottom, or 1 mole on top and 16 grams on the bottom. We're going to pick which factor is going to help us solve this problem. First, we need to look at the problem. What's our starting measurement? 9 moles of CH4. So we're going to choose the factor that has 1 mole of CH4 on the bottom. The arithmetic is 9 times 16 divided by 1, which gives us 144. That's the number of grams of CH4 in 9 moles. Does that make sense? It does, because our factor has moles of CH4 in the denominator. It cancels out the moles of CH4 in our starting measurement and leaves us with grams of CH4. It also makes sense because the number of grams is much bigger than the number of moles. 16 grams in 1 mole, the number 16 is much bigger than the 1. So the 144 grams in 9 moles, the number of grams should be much bigger. One more example. How many grams of ammonia, there's the formula for ammonia, are in 2.5 moles of ammonia molecules? We're not given the molar mass of NH3, ammonia, so we need to figure it out. Here it is. It's 17.0 grams per mole. We can write the 17 grams on top and the 1 mole on the bottom of our factor, or we can do it the other way around. The factor we choose is going to depend on what our starting measurement is. We're starting with 2.5 moles. We want to go to the number of grams. So we're going to choose the factor that has moles in the denominator. 2.5 times 17 divided by 1 is 42.5. That's the number of grams of ammonia in this many moles. Does that make sense? Yes, the units cancel out correctly. And the number of grams is bigger than the number of moles. So we've used molar mass to start out with a mass of a sample and figure out how many particles, how many moles of particles are in that sample. We counted the particles. Or if we already know how many moles of a substance we have, how many particles we have, how many grams will they weigh? We can figure that out also. Over and out.